So here, even though this lesson is about the second law of thermodynamics, it's important to understand exactly what the third law is as well. The third law of thermodynamics, also known as the Nernst heat law, states that as the temperature of a system tends to absolute zero, its entropy tends to decrease. For instance, when the entropy of a system goes to 0 Kelvin, which, by the way, is unattainable, there are fewer and fewer ways to rearrange particles, and hence entropy goes to 0. To calculate entropy change for a chemical reaction at, say, a specified temperature above 0 Kelvin, we only need to know the knowledge of the entropies of a substance above 0 Kelvin. And we can do that by integrating heat capacity, how we calculate enthalpy, from 0 to whatever temperature that we want. Usually, we calculate it all the way to 298 Kelvin, something known as standard entropy. Here in thermodynamics, we consider room temperature as 298 Kelvin. So let's look at another example. How do we calculate total entropy change of oxygen from 0 Kelvin all the way to 298 Kelvin? We know two things about oxygen. Its melting point is 54.36 Kelvin, and its boiling point is 90.19. So what that means is, before 54.36 Kelvin, oxygen is a solid. After 54.36 Kelvin, it becomes a liquid. And after 90.19 Kelvin, it becomes a gas. For us to calculate the standard entropy for oxygen, we must take into account entropy change while it is melting, entropy change while it's boiling. We must also add its entropy as a solid, its entropy as a liquid, and its entropy as a gas. Here's a hot tip though. Standard entropies have been calculated many times over for standard compounds such as oxygen and are available in reference books. It's however important for you as material scientists and engineers to understand what's going on below the hood. So let's try to calculate entropy changes in chemical reactions. Let's consider for a moment this reaction where silver reacts with chlorine gas to form silver chloride, a solid. So the general way to calculate entropy is the same as calculating enthalpy. You take the sum of the standard entropies of the products minus the sum of the standard entropies of the reactants. And this is the general heuristic. So, how do we calculate entropy change for the formation of silver chloride at 298 Kelvin? First, consider the product. And substitute standard entropy of silver chloride accordingly. Next, you subtract the reactants. This over here is the standard entropy of silver, and this over here, the standard entropy of chlorine. Note the half, which represents its stoichiometric ratio. Doing the simple math, you will get this entropy change for this reaction to be 57.7 joules per mole Kelvin. From here, we can derive a few things. Firstly, it's moved to a more ordered phase. You have reacted silver with a gas to form silver chloride, which essentially is a crystal structure. Secondly, there is a reduction in the gas phase, as we have used essentially one chlorine atom to react with silver to form silver chloride, and that has essentially liberated other chlorine atoms and allowed them to form elsewhere. So entropy changes really give us a lot of insight as to both the direction and to exactly what happens to a reaction. So how do you calculate entropy change in chemical reactions beyond standard entropy? The procedure is very similar to calculating enthalpy. First, take standard entropy and add it to the integral to your desired temperature. Remember, take the constant heat capacity of your product minus the constant heat capacity of a reactant, taking into account the total mass of both your product and your reactant.